Welcome to Hartman Math. Today we're going to look at graphs of other trig functions besides sine and cosine. Prior to that, a little trig warm-up. Go ahead and pause the video here and work through problems 1 through 5. All right, number 1, looking for cotangent. You can do it either by sketching it out or you could use Pythagorean identity. But we do get the square root of 7 over 3. The exact value for the secant of negative 10 pi over 3. And I think rotating in the negative direction, negative 6 pi over 3 takes us once around. And then 4 more pi over 3s puts us in quadrant number 2, coterminal with positive 2 pi over 3. And secant being the reciprocal of cosine, since cosine would be negative 1/2 due to the x-coordinate, secant's negative 2. Tangent of 5 pi over 6. Also quadrant 2, pretty much almost straight across. It's one of those pi over 6 reference angles, so it's long going on the x, short going up on the y. So we're thinking of the coordinates negative root 3 over 2, comma, positive 1/2. And the tangent of y divided by x be negative 1 over root 3. Cosine, given that, and that we are in quadrant 2, find the tangent. And again, another one that we could sketch, or we could use a Pythagorean identity to find sine of theta. And once we do that, find tangent. Either way, but it does come out to be negative 2 root 2. And then from 0 to 2 pi, where is cosine negative 1? Where is the x-coordinate on the unit circle negative 1? Only one place theta would have to equal pi. All right, lesson 4.6, graph of other trig functions. So we're talking about tangent, cotangent, cosecant, and secant. We're going to start with tangent. We've got pi over 2 marked here. And so we're going to be asking things like, what is the tangent of negative pi over 2? If I think of that, it's something divided by 0. So that's undefined. So when we have an undefined value, we have a vertical asymptote. What about at negative pi over 4? So rotating down into quadrant 4, root 2 over 2, comma, negative root 2 over 2. Quotient, the y divided by the x, negative 1. So negative pi over 4, comma, negative 1. What's a tangent of 0? 0. Tangent of pi over 4 is where we're at. Root 2 over 2, comma, root 2 over 2. So dividing those, you get 1. And tangent of pi over 2 straight up, where our coordinates are 0, comma, 1, so we get 1 divided by 0, and that is also undefined, vertical asymptote. So as far as our shape here, we want to stay within the asymptotes, get close to them, pass through these points, and it turns out that the shape of the tangent graph looks very similar as a base function to the shape of y equals x cubed. So it looks like this. It only changes the direction of the bend, meaning a point of inflection, at the origin. So it bends this way, hits the origin, then bends this way. So you can't hit here, bend, bend, bend. It does not behave that way. So it looks like this. This would be one period. We could extend, we could copy this, put another one here, put another one here, put another one over here, and we can keep going in both directions. The period is the distance between the asymptotes. This is pi over 2, that's pi over 2 added together is 1 pi. So that's a little bit different than sine and cosine. The domain, well, all these are good, but no x values here, no x values here. They're separated by pi, so we could say x cannot be pi over 2 plus any multiple of pi where n is an integer. Okay? Meaning x cannot be pi over 2, x cannot be pi over 2 plus pi, x cannot be pi over 2 plus 2 pi, pi over 2 plus 3 pi, and so on, and going backward. The range, forever down, forever up. All real numbers for the range. And the vertical asymptotes, very much connected to the domain. We just say x does equal these things here, and the next one over. So x would equal pi over 2 plus n pi, where n is an integer. So some of our generic functions, a times tangent of b times x. We don't actually talk about amplitude because there's no highest point, that kind of thing. But a is, again, stretch and possibly a vertical reflection. Period, because the period is pi, we determine that pi divided by b, as our base period was pi. All right, example number 1, sketch the graph of the tangent function. Y equals negative 2 times the tangent of x over 2. First thing we need to go after, and the most important on all of these graphs, is to be able to correctly identify the period. So we're talking about pi divided by b. X divided by 2 is the same thing as 1/2 times x. So b is 1/2. Pi divided by 1/2. Probably want to think of doing pi times the reciprocal of 1/2, which is why we would get 2 pi. And then we're going to go ahead and kind of set the scale and set the asymptotes. Going back, you kind of look, the tangent function is kind of centered about the y-axis. Half the period to the right, half the period to the left is where we set the asymptotes. So here, half the period to the right, you can set it at pi and negative pi, and the distance between those would be 2 pi. And then, due to our scale here, I could just have this be 2 spaces up, or I could just clearly mark this as 2 units here. And then over here, usually tangent, as we saw in our parent function, was down here at the -1. We would stretch that, but as we're stretching by -2, that's also flipping it. So it's flipping it to 1, but then stretched to 2. The point would go here, and then the origin, and then here. So now, instead of tangent being increasing, like it is as a parent function, our reflection's causing it to be decreasing. Again, make sure we draw it nice and smooth, with it only changing the direction of the bend here, where it goes from concave up to concave down at the origin. All right, cotangent base function. Cotangent of 0. The cotangent of 0, again, if we want to cotangent is x divided by y, so 1 divided by 0, undefined. Then we get to, well, if pi is out here, then we've cut it into 4 pieces. This is pi over 4, which is here. So x divided by y is 1. And then we get to pi over 2. X divided by y is 0. Over here, same thing, but negative, as the x-coordinate is negative, so -1. And then we finish over here at pi. X divided by y, again, can't divide by 0, undefined. So a little bit similar. It's got definitely some similarities with the tangent. It's got the asymptotes. They are placed the same distance apart, so you're going to see our period's going to be the same. But notice that the asymptotes are shifted. I actually find the cotangent graph easier to graph because for the parent function, one of the asymptotes is the y-axis. One of the asymptotes is right on the period, which is pi. And then it's just a decreasing function as a parent function compared to tangent. The domain, x cannot be 0, x cannot be pi, another pi over, x could not be 2 pi, x could not be 3 pi. X cannot be any multiple of pi as long as that multiplier is an integer. Range, pretty clear. And then again, the vertical asymptotes tied to the domain. X does equal, as our vertical line, 0 and pi and 2 pi and so on. Example number 3, sketch the graph of the cotangent function. Quite a bit going on in this one. First thing we're going to want to go after is the period. The period is pi divided by b, pi divided by 2. The phase shift is always c divided by b, no matter what the function is. C is pi over 4 divided by 2, or you could think of that as pi over 4 times 1/2, the reciprocal. We do get pi over 8, and it is positive. So we will be going to the right. If we did want to factor out the 2, we would see this. Then you can see kind of how the phase shift connects to the factored form. Let's make sure that our scale, it's already labeled here, so I'm hoping that it's good, but we should probably do some side work to kind of check it out. Our period, pi over 2, is equal to 4 spaces. We want to get to pi over 8, see how that fits, so we'd have to divide this by 4. Divide by 4. Hey, our phase shift is going to be 1 space, that's a whole number. We should be good to go. All right, so speaking of that 1 space, and we're going right, we would normally have vertical asymptotes on the y-axis and the period. We are going to shift right 1 space with both of those. Okay? If you were doing left vertical asymptote and right vertical asymptote, you would set our expression here or here, but probably here, equal to where they normally are, 0 and pi. Because that would always tie back to the parent function. But as I said, I would just think, okay, it's going to be on the y-axis and the period, and I'm going to shift them right 1 space. And then our a value is 1, so no flip, no stretch, should be good. Cotangent is going to start here above at 1, and then halfway be on, and then below. Those are where the points go. And we are showing 1 full period. If you were required to show more, we just copy this, paste it to the left side, or paste it to the right side, and we can have multiple periods. Cosecant function as a parent function. Well, remember that cosecant is the reciprocal of sine, so it would probably be a good idea to remember what the sine function looked like. So sine had a period of 2 pi. It started on the midline, and then went up, and then came back to the midline, and then down, and then back to the midline. So we're thinking of our helper function here, which is the sine function. Something like that. We could extend it out to really see what's going on. And then for cosecant, remember the cosecant is just the reciprocal of all these values. So here, the value there, and here, and here, and here, and here, the value of the sine function is 0. Cosecant is the reciprocal. So if we take the reciprocal, can't take the reciprocal of 0. That would be 1 over 0. Can't divide by 0. That's where we're going to get a vertical asymptote. So everywhere that sine has an x-intercept, cosecant has a vertical asymptote. And then if we're looking at this section here, right there, just past that asymptote, we have a very small value. Very small. When you take the reciprocal of a very small value, actually get a very large value. So we'll be way up here. And then as we get a little bit bigger, we're going to get smaller until we get to here. The highest value here is 1. What's the reciprocal of 1? It's 1. We're going to have a point right there. So it turns out we're going to have a bunch of what I'll call mini parabolas and all these peaks and valleys below here, above here, below here, above there, kind of connecting. If we needed to just do one full period, it's one up parabola and one down parabola. Okay? They're not quadratic, it's just that's the resemblance of the shape. So we'd really kind of just show this might be our one full period right there. All right, so the period, it does complete an up and down within 2 pi. It's our period. The domain, again, we can't have x values on these asymptotes, so x cannot be 0 or pi or 2 pi or 3 pi. I think we've seen that back from cotangent. So actually going to be the same domain as cotangent. The range, forever up, it doesn't actually always kind of go forever down because in here there are no points in this middle section. We got all these and we got all these, but nothing in the middle. So we got to go low to high, negative infinity up to 1, and negative 1, and then 1 to infinity. That's our range. So do 2 different pieces to that. And then our vertical asymptote connects to domain. The secant function clearly connects to cosine, so we might graph cosine as our helper function. Remember, cosine started on the y-axis at its maximum point at 1 and was the wave from there. And once again, kind of the same concept as the cosecant. Wherever we have x-intercepts, we're going to place vertical asymptotes. And then mini parabola, mini parabola, mini parabola, mini parabola, mini parabola. So if you're needing to show 2 full periods, it could be that you might just want to show kind of like more than 1 full period if we're just trying to do 1 period. It's typically here to here, so kind of this part, and then this one and that part. A lot of people don't like that part, so they'll just extend and just show all of this and all of this. And if it's showing more than 1 period, that's not a problem at all. Period is again same as it was for cosine. Domain, x cannot be negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2. So it kind of turns out to be the same as tangent. Range, negative 1 and below, positive 1 and above. Vertical asymptote. Now, one important thing as we start to now manipulate and get other kinds of cosecant and secant functions, important to set the vertical asymptotes before you do any vertical shifting. So if you have to shift up 3, say, well, the cosine function doesn't hit the x-axis, doesn't matter. It's based off of before you would shift up, you need to set the asymptotes. Example 4, sketch the graph of a cosecant function, period, phase shift, and so on. All right, so period is going to be 2 pi, as this connects to sine, 2 pi divided by b, so 2 pi divided by pi. You get 2. The phase shift is c, which you got to think opposite, so this is negative pi over 2 divided by pi, that would be negative 1/2. So we are going left on that one. All right, we do have the scale set, but let's see if that's actually accurate. We're going to do our side work. We're hoping that the period 2 will be equal to 4 spaces. If it doesn't work out, remember some other multiple of 4 for the number of spaces. Want to get to 1/2, well, if we go just divide by 2, 1 unit here would be 2 spaces, and then if we divide by 2 again, we get 1/2 is equal to 1 space. It's going to be our phase shift. So we might think of initially graphing the sine function that goes with this, where we're starting sine. It would normally start here, but we're going to start one space to the left, and it would normally end here, the period being 2, we would end here, one space left. So start and end for our sine function. There will be the 1. X intercepts, we're going to set our vertical asymptotes. And then mini parabola, one full period for example number 4. That's it for today. I'll see you next time.